Because we're using the number again.
Yes. How about excuse me, I only said.
Well, piss in 3, 2, 1.
Oh, well, the way you turn on your give her a little big old smile.
Okay. Am I on?
No.
Am I on?
Oh, there you go.
There we go.
Holy crap.
Thank you. Okay. Back to this.
Crank me up.
Okay. Ooh. So, because we're using this number again, because it said use your answer from 1A, we have to use the unrounded number. So we've got molecules of ammonia. How many nitrogen atoms are in one molecule? 1. So if I multiply this by the ratio of one nitrogen atom for one molecule of ammonia, because molecules of ammonia are on the top in the first value and on the bottom in the second value, they cancel. So I have 1.204 times 10 to the 24 nitrogen atoms, which rounds to 1.2. There is an infinite number of significant digits in 1 because it's a count. So you go back to your original data, which came in question 1A, and that was 2.0 moles. So 2.0 had 2 sig figs. So this answer has 2 sig figs. Okay, so what would be the ratio then for hydrogen? Matthew? Look at ammonia. 3. So 1.204 times 10 to the 24 molecules of ammonia times 3 hydrogen atoms for every 1 molecule. Again, molecules on the top and the bottom, so it cancels. So we've got 3.6 times 10 to the 24 hydrogen atoms. Calculate the amount, so we're looking for the number of moles. We always know Avogadro's number. It's hydrogen chloride, so it's that number of molecules for 1 mole. So N is equal to big N divided by NA. So these answers are in Schoology, in the green folder. So how many do we have? 100, right? There's 100 moles. Oops. Okay, so dimensional analysis uses ratios or fractions, and when you set it up, you can only set up by multiplying. We're multiplying fractions. So that's the setup. So what do we want to find in this answer for 2B? What is the question looking for? The number of moles. Does any one of those values up there have moles in it? Anywhere? Do you see the word MOL? Tamara, where is it? Yeah, the bottom part of the ratio for Avogadro's number. If we want mole to be our unit, it needs to be on top. What you're going to do when you set up dimensional analysis is you're going to put that value for the mole first. So find wherever your unit answer is, that goes first, and it has to be on top. So we want mole. Don't write anything down yet. So we would put this in like this. That's how we would start it. So mole comes first. We don't want molecules though. So we've used this. The other value has molecules in it. So if we multiply these numbers, molecules are going to cancel. So in your calculator, whatever's on the top, you multiply. Whatever's on the bottom, you divide. So you would do 1 times 6.02 times 10 to the 25 divided by 6.02 times 10 to the 23. And guess what your answer is? 100. So you don't even have to remember formulas. All you have to know are what are the units for your answer. Do you want to do another question like this? Okay, do you want to write this down so you have it in your notes? Is there any ratio that we have that has particles and moles in it? A ratio. We use it again and again and again, we use this ratio. But we're talking ratio, so some number.
What's this weight called?
Dimensional analysis, DA for short. Avogadro's number. That ratio always contains particles and moles. You're going to keep using it. As long as we're talking about particles, you're going to use Avogadro's number. So we've got iron. It's an element. So Avogadro's number is already in atoms. Yes. Is it already on the top or is it on the bottom? It's on the top, so all we need to do is leave it alone. So we're going to have 6.02 times 10 to the 23rd atoms over 1 mole. When you set up dimensional analysis, you're only multiplying each thing when you set it up times 0.0718 MOL. So when you type it in your calculator, you're going to have 6.02 times 10 to the 23rd times 0.0718. Pretty awesome. And the answer would be unit that we're looking for in our final answer. Atoms. So which one of those 3 pieces of data has atoms in it? First, second, or the moles? First. So first we're going to write down 4 atoms per 1 molecule of ammonia. We need to get rid of molecules of ammonia. So what of the 2 things that are left have molecules in it? The Avogadro's number. Is the way it's written, will that molecule cancel the molecule in the first ratio? Where does molecule have to be in the next ratio in order to cancel that one on the bottom? You said it. Say it louder. On the top. It's got to be on the top. So we're going to use it exactly as it is. It can only cancel if it's on the top and the bottom. So now, if we did this, our answer would be atoms per mole. We want just atoms. So we have another one, and that's 3.30 moles. So our units for moles will cancel. So in your calculator, you would have to put 4 times 6.02 times 10 to the 23rd times 3.3 divided by anything on the bottom. And you would have to do each one separately. Obviously, when you divide a number by 1, it doesn't do anything, but sometimes you're going to get to a place where these numbers on the bottom are not always 1, okay? So anything on the top, take the numbers and multiply. Anything on the bottom, each one of them is divided. And so your answer is, anybody? 7.946 times 10 to the 24. Anybody else get that number? Yes? Okay, so how many significant digits can we have in our final answer? This ratio here has an infinite number of sig figs because they're counts. This ratio here, infinite number of significant digits, it's a count. So you have to go back to this to figure out significant digits, and it has 3 because that 0 is trailing and it's after a decimal place. So your final answer would be 7.95 times 10 to the 24 atoms. The first ratio was 2 nitrogen atoms for 1 copper 2 nitrate. 2 nitrogens because there's a bracket 2. We use this ratio first because it's got the unit that we're looking for, atoms. So multiply this. We need to get rid of copper nitrates, and that's really a formula unit, not a molecule. So Avogadro's number says that we have that number copper nitrates in 1 mole. And we have 2 moles.